In this video, we're going to dive into the world of parametric design and explore how to create a precise dovetail joint using Freecad. A dovetail joint is a woodworking joint that is known for its strength and resistance to coming apart. It's commonly used in furniture making and other woodworking projects. By inputting values into Freecad, we can generate a parametric sketch that will automatically adjust the dimensions of the dovetail joint based on the changes we make to the parameters. This means that we can easily experiment with different designs and create custom dovetail joints for any project. We'll walk through the step-by-step process of creating this parametric dovetail joint in Freecad, from creating the sketch to generating the 3D model. By the end of this video, you'll have a solid understanding of how to use Freecad to create precise and customizable dovetail joints for your woodworking projects. To ensure a perfect fit, we'll be using a mathematical formula to calculate the exact dimensions of each dovetail. This formula, shown here, takes into account the overall width of the board, the number of dovetails, and the desired offset and size of each pin and socket. I have added chapters, so if you're not interested in this part, you can skip it. The formula is a cornerstone of parametric design in dovetail joinery. It allows us to create precise and repeatable joints, even when modifying the overall dimensions of the workpiece. This flexibility is invaluable for custom woodworking projects. Let's create a variable by clicking the varset icon. Close the pop-up window. In the Data Properties, right-click and choose Add Property. Make a new variable, making sure it's a length. Our first variable is the board width, which is L in the diagram. We'll follow the same steps to create the next variable, the board thickness. I've listed all the necessary variables. I've sped up the video for efficiency, but please ensure you choose the appropriate variable type: length, angle, or integer. The joint will consist of two boards that may have different lengths. This is why two variables are defined for the board lengths. The socket dimension will be customizable, whereas the tenon dimension will be calculated based on the formula previously shown. Each variable has been suffixed with the corresponding letter from the preceding diagram. Offset from the edge shows how much space there is between the board edge and the first socket. We will now create the variable for the number of sockets, which is an integer. Please ensure you select the integer data type. The final variable to be created is the socket angle. Please select the appropriate angle data type. We can now input various values for the variables, except for the tooth size, which will be calculated using the preceding formula. For your convenience, I have attached the formula alongside. To reference a variable within the formula field, you must begin by typing varset followed by the variable name. Please follow the formula I am entering step by step, ensuring that you do not omit any parentheses or signs. The calculation is done by subtracting twice the offset from the board width, then subtracting the total width of the sockets, number of sockets multiplied by socket size, and finally dividing the result by the number of sockets minus 1. The final result should be a value of 25 millimeters. Once we have completed this laborious step, we can proceed to 3D modeling, where the formula will be brought to life. Within the Part Design workbench, create a new body and a new sketch on the YZ plane. Utilize the Rectangle tool to draw a rectangle, positioning the first corner at the origin. We will sketch half of the board, which may seem unconventional. Given the symmetrical nature of the joint, performing an array followed by a mirror operation is not feasible. Consequently, the input length corresponds to half of the board length 1 variable, while the height corresponds to the border width variable. Once the sketch is fully constrained, we can close it and create a pad operation with a thickness equal to the board thickness variable. Having created the face, we can now generate a sketch on it to define the dovetail tooth. We will employ the external geometry tool to project the top edge of the board into the sketch. The polyline tool will then be used to sketch the offset and the tooth profile. We convert the line of the offset to a construction line. To constrain the sketch, we will use the Make Vertical function and keyboard shortcuts like S for symmetrical constraints and D for dimensional constraints. We will now define the angle of the dovetail joint by using the Dimension tool to select the two lines and create an angular dimension. The value of this dimension will be set by the socket_angle variable. Replicate the steps to create an equivalent angular constraint on the opposing side. We will now define the height of the offset from the origin. While this approach may seem unconventional, it prevents recalculation errors in Freecad. Therefore, we will input the value as the board width, variable minus the offset from the edge. We will define the socket size in the same manner, using the value of the board width, variable minus the offset from the edge, and minus the socket size. While this approach may seem non-standard, it prevents recalculation errors. We will now define the socket depth. It corresponds to the board thickness. We will define it from the origin, so the value must be equal to the board length 1 variable divided by 2 minus the board thickness. Before closing the sketch, be sure to convert the dovetail symmetry line into a construction line. Generate a through-all pocket feature. In the feature tree, activate the linear pattern tool on the existing pocket feature. Pick Z-axis as the direction, check reverse, and choose offset. Set the offset to the socket size plus the dent size. For the number of copies, use the number of sockets variable. If you have successfully completed all the steps, you can modify the various values in the variable set to verify that everything functions as expected. We will now perform a mirror operation on the part. Unfortunately, we cannot remain in the part design workbench as it does not support creating a linear pattern followed by a mirror operation. Therefore, switch to the part workbench and with the body selected, click on the mirror tool. Perform a mirror operation using the XC plane as the mirror plane. Subsequently, combine the two solids through a Boolean union. We will now create the second board. Return to the part design workbench, create a new body, and sketch on the XY plane. Using the rectangle tool, draw a rectangle with one corner coinciding with the origin. Apply a dimension using the D key, setting its value to half of the board length 1 variable. To define the thickness, create a dimension from the origin and set its value to half of board length 1 minus the board thickness variable. Finally, create a dimension for the board length 2 variable. Select all sketch elements and perform a mirror operation, ensuring the Add Constraint option is checked. In the property tree of body 001, select the Allow Compound option and set it to True. Then, perform a pad operation using the value of the board width variable. We will now create the dovetails on the second board. To achieve this, select Board 1 and navigate to the Draft Workbench. Utilize the Clone tool, and then, in the Part Workbench, perform a Boolean subtraction operation between body 001 and the clone. Select Board 1 and create a new clone. Using the Move tool, position the clone at the end of body 001. In the Clone Placement Data Properties, input the value of minus board length 2 plus board thickness. Copy the formula using Ctrl+C. Then, create another clone, and in the Placement Data Properties, paste the formula using Ctrl+V. As a final step, select the cut body and then the last clone. Perform a Boolean subtraction operation in the Part Workbench. Congratulations! You have now created a fully parametric box with dovetail joints. Feel free to adjust the various parameters to verify that everything functions correctly. I hope this tutorial has been helpful in your Freecad journey. If you have any questions or concerns about this model, please don't hesitate to leave a comment. Thank you for your attention.